Hello and welcome. Today is step 3, 1993, question 4, and we're going to be looking at some beautiful series. Okay, so these are the series. Of course, pause the video and try it for yourself. So the first one. Okay, so often with these questions, it's much simpler to write it in sigma notation. So I'm going to do that straight away. So part I. So I'm just going to write it in sigma notation. It's already given me the general form. So sum from infinity, n equals, I'm not quite sure what n is going to start from yet, so I'm just going to write out the general term. 2n plus 1, a half, and that's to the power of 2n. Well, of course, n is going to have to be 0, so I can get that 1 from my first term. Now look at this, okay? So there's some very, very simple things to try and find the value of these series that you can look for. So you can look for geometric, look for telescoping series, that's when the terms cancel, and look for partial fractions. Okay, so I see a power here, so I'm thinking of geometric, although I can't obviously apply that yet because I have this factor of 1 over 2n plus 1 here. Okay, so now if you stare at that long enough, perhaps you might see that the power we're raising to here is similar to the number that we're dividing by. And that's quite similar to integration. Well, it's almost exactly like integration, except in integration we have the same power here as what we're dividing by. So I'm just going to take out here, I'm just going to rewrite this as n equals a half divided by 2n plus 1. And here I'm going to write a half to the 2n plus 1. Well, now I've written a half to the 2n plus 1, so I have to pull out a half to the minus 1 so that when I add those powers I get back to my original, the original thing that I had. So I'm just going to quickly rewrite that. Half to the minus 1 is the same as writing 2 times. Okay, now we see that this is an integral, and don't worry if you haven't seen this before. Okay, but I'm going to rewrite this as 2 times, well it's, still that infinite sum, it's the infinite sum starting from n equals 0, but now I'm going to write the integral. Well, it'd be the integral of x to the 2n, because I'd raise that power, so I'd get x to the 2n plus 1, and then I'd divide, so I'd get x to the 2n plus 1 divided by 2n plus 1. And of course that's just fixed to x, and now I need to consider my limits. Okay, well I only have one thing here, I just have half, okay? And I have nothing else. I'm going to have 0 on the bottom of my limit to make that vanish, that second term vanish. Okay, well now, if I look here, in fact what I can do with an integral sign is I can pull it out. Okay, I can interchange integral signs with sigma, with the summation. So I'm just going to go down here, it's okay. So it's 2 times, well I'm just going to bring that integral sign out to the front. And if you're not sure about this, write out a few terms and you'll see that this works perfectly fine. So now it's the infinite sum, n equals 0, x to the 2n, and of course, I mean this is with respect to x, this is brackets here. Okay, so now I have x to the 2n, it's a summation. Okay, well I'm just going to rewrite this slightly differently, so it was x to the 2n, but I'm just going to write it as x squared to the n, which is the same thing. And now we take a step back. Beautiful, now we can apply the geometric sequence formula. So this is an infinite sum, so it's the infinite geometric series formula, which is a over 1 minus r. So here, when I put n equals 0 in, I get a equals 1. R, a common ratio, is x squared. So this is going to be equivalent to writing 2 times the integral from a half, 0, keeping this the same, and this is going to be a over 1 minus r, is 1, r is x squared, and this is with respect to x. Okay, well now what do I do here? Well, see, this is the difference of 2 squares, so I'm going to apply partial fractions. So just as a side, let's apply this here. So we want to write 1 over 1 minus x squared in the form, well, first of all, I know that I can write this as 1 plus x, 1 minus x, and that's just from partial fractions. Sorry, that's just from the difference of 2 squares. And then I want to write this in terms of partial fractions. So I have 1 over 1 plus x times 1 minus x, and I want to write this in the form a over 1 plus x plus b over 1 minus x. Okay, and the way you do that is you times up, so I'm going to get 1 equals a times 1 minus x, and then I times up by the 1 plus x, and then you sub in values, so sub in values x equals 1, and x equals minus 1, and when you do that you see that a equals a half, and so does b. Okay, meaning that we can rewrite this as a half over 1 plus x plus a half over 1 minus x. So I'm just going to rewrite this here. So this is going to be 2 times the integral from a half over 1 plus x plus a half over 1 minus x, and that's with respect to x. Well, the 2, I'm going to bring that 2 inside now. So now this 2 times is with the half, so just give me 1, so that's just 1 over there. And again, that's just 1 over. Well, now this is going to be the natural, I'm going to get the natural logarithm. If the top is the differential of the bottom, the integral is the natural logarithm of the bottom function. So I'm going to get, so it's going to be the natural logarithm of the modulus of 1 plus x. And here we have a minus sign, so this is, so I could rewrite this as minus 1. So I'm going to get minus the natural logarithm of 1 minus x, and remember the modulus sign here, and then I'm just going to write this. So this is evaluated between x equals a half and x equals 0. Well, I can combine this using my law, using the law of logs. So I get modulus of 1 plus x divided by 1 minus x, and half and 0. So when I sub that in, I get here, I get the natural log of 1 plus a half is 3 over 2, so it's 3 over 2 divided by a half, and that's modulus sign. And then here, when I sub my limits in, I'm going to get the natural logarithm of 1 plus 0 divided by 1 minus 0, so that's going to be the natural logarithm of 1, which is 0, so that will vanish. I'll just neaten this up. So I'm just left with this, and this term, in fact, is just the natural logarithm, modulus of 3, well I can just get rid of that, and it's just the natural logarithm of 3. Okay? Okay, so let's move on to the next part. So for part II, again, I'm going to write this in sigma notation. So again, just they've already given me the general form, so it's k equals 0, and I have 2x to the 4k minus x to the 4k plus 1, and the final term is minus x to the 4k plus 3, given that the modulus of x is less than 1. So straight away I'm thinking, oh, I might have to apply geometric series there, so the geometric formula. So I see that, well, there's x to the 4 that's common in all of this, so let's just take x to the 4 out. So I get x to the 4, oh sorry, there's x to the 4k that's common in both. So it's 2 minus x squared. Well, now look at this term, and this in fact is independent of k. So when k is 0 and it's 1, this is going to be present in every single term, okay? So this can be treated as just a constant multiplier, so I'm going to go over here. So this can actually be brought out of the summation, because it doesn't depend on k. Okay, so now we just have the summation from 0 to infinity of x to the 4k, okay? And now, this is a geometric series, okay? And to make this very explicit, you can just rewrite this, instead of saying x to the 4k, just say x to the 4 to the k, okay? So, we have, just applying our formula, and again, you might want to write that, we know that the modulus of x is less than 1, and therefore the modulus of x to the 4 is also less than 1. Okay, so applying the series, so we have 2 minus x squared, and then the formula is a over 1 minus r. A in this case is 1, so it's just times 1, over 1 minus r, where r is a common ratio, and in this case it's x to the 4. So this is our final answer for part 2. Okay, so now let's go on to part 3. So with this part, it's already written in sigma notation, which is nice. So the first thing I'm going to do here is, well, it might be nice to group the 2 and the 3. So where this is infinite series, r equals 2, so I'm just going to group the 2 and the 3 together. So I get r, well let's choose the power to be r minus 1. Well now I'm going to have 2 to the power of r minus 1, when originally I had 2 to the power of r minus 2. So I'm going to times this, and I'm going to force 2 to the minus 1 out. And again, 2 to the minus 1 is 2, so I can just rewrite this as 2, and write this at the front. Okay, so it's 2 times the sum from infinity, r equals 2. Well now this, okay, what do you see here? We see r minus 1 and then r. Well that's similar to differentiation. So So in the first part we had something that looks similar to integration, and now we have something that looks similar to differentiation. Okay, we've brought down the power and we've decreased the power by 1. Okay, so now I can rewrite this. Well, we already know how to do differentiation in terms of a variable, so just write the infinite sum, r equals 2. Well, this is d by dx, the differential of x to the r, evaluated at 2 over 3. Okay? Well, similarly with the integral, we can actually bring the differentiation out to the front, in front of the summation. So we have 2 times the differential, and again, if you're not sure about this, write out some terms and you'll see. But r, so it's the summation from the infinite summation, r equals 2, and now we just have x to the r, and of course, this is evaluated at 2 over 3. This bar means evaluated at, so it's the differential of this. Okay, now I see that this is another geometric series. Okay, so here I can apply my formula. So a in this case is x squared, so it's going to be, I still have that 2, and then it's the differential of x squared over 1 minus r. In this case, r is x. Okay, and of course this is evaluated at 2 over 3. Okay, so now I just need to differentiate this. Recall just for 1 second that if we have u over v, and this is 2 functions of x, and we want to find the differential, this is vu minus uv, vu dash minus uv dash over v squared. Okay? So then applying that here, so this is just a note, so just note this. Okay? So, differentiating this with respect to x, I'm going to get 2 times. So I have v, which is the bottom thing, 1 minus x, and times it by the differential of the top thing, and minus the top thing, and then I times by the differential of the bottom thing. The differential of the bottom thing is minus 1, so this becomes a plus, and then I divide the entire thing by 1 minus x squared, and this is evaluated at 2 over 3. Okay? Well, now we can just plug in the numbers. Okay, so we get this is equal to 2 times, when I put 2 over 3 into here, I get 1/3 times 4 over 3 plus 4 over 9, all divided by 1 minus 2 over 3 is 1/3, and that's squared. And when you work this out, this is going to be equal to 4. Okay, so let's get on to the final part, part 4. So we have this infinite series. And as I said at the start, you want to look for geometric partial fractions telescoping. This to me screams partial fractions. Okay, so I want to rewrite 2 divided by r times r squared minus 1. And I want to rewrite this in the form a over r plus b over, we see here, this is the difference of 2 squares. So I want to write this as b over 1 plus r. And finally c over 1 minus r. Okay? And then, well, let's just try this. So it's 2 equals a, I'm going to times by 1 minus r, 1 plus r, and then here b I'm going to times by r and r minus 1, and then c here I'm going to times by, c is going to times by r and r plus 1. Well, let's try r equals 1, so try r equals 1. We get 2 equals, this is going to vanish, this is going to vanish. Here I'm going to get 2 times 1, which is 2, so I'm going to get 2c, which implies that c equals 1. Okay, so now let's try r equals minus 1. Okay, so here it's going to vanish, here it's going to vanish, and here I'm going to get b times minus 1 times minus 1 minus 1, which is minus 2. So altogether this is going to be, of course this is equal to, sorry, I have to rewrite this. So try r equals minus 1, so we have 2 equals b times minus 1 times minus 2, which equals 2b, which again implies that b equals 1. Okay, finally let's try r equals 0. On the left hand side we're still going to have the 2. Okay, so here is going to vanish, here is going to vanish, and we're just left with a times minus 1 times 1, okay, which is minus 1. So this implies that a equals minus 2. Okay, so now I can rewrite this as, this is going to be equal to minus 2 over r plus 1 over r plus 1, and plus 1 over r minus 1. Okay? So now let me just rub this out. So, I'm going to rewrite this sum in terms of these partial fractions. Okay? And this screams telescoping series, or method of differences, where things look like they're going to cancel here. So in this term, I'm just going to write this as minus r minus r. And hopefully this might make the cancelling a bit clearer. So I have r equals 2, I'm just going to write minus 1 over r minus 1 over r for this term. And then it's still plus 1 over r plus 1, and I have plus 1 over r minus 1. And now just write out a few terms, see what we're going to get. So r equals 2. We're going to get minus 1 over 2 minus 1 over 2 plus 1 over 3 plus 1. Okay? This is the first term. Plus, okay, so the next term, r equals 3. So I get minus a third plus a fourth and plus, so r equals 3 here, so this makes this 2. Yeah. And then again, just do this again. I'll do this one more time. So now we'll try r equals 4. So we get minus a quarter. R equals 4 here, you get plus a fifth. R equals 4 here, you get plus a third. And then it's plus dot 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 dot. And you might have to take your time with this and just really consider which things are going to cancel. Okay, so we see that these two terms, each two term, it cancels with one thing before it and one thing after. So see, for example, this third, one of the thirds cancels with a third from the previous line, and one of the thirds cancels from the third from the next line. So all of these terms in the middle are going to cancel. Right? And likewise with these cancel with, so this term cancels with the term on the next line. Okay, so all of this is going to cancel. All of this is going to cancel, except for perhaps some of the terms on the first line. So we see a minus a half. Okay, so one of the halves gets cancelled. Okay, but we're still left with minus a half. Okay? And then the third, the third's cancelled perfectly. And the 1, we're still left with the 1. Nothing cancels with the 1. Okay, so this are the only things that are left over after everything cancels. Okay, so this cancels with this, and this cancels with this, and this cancels with this, which will cancel with something later, and the fifth will cancel with something later, and the half cancels with one of the halves, and the third, similarly, already cancels with this. So we're just left with 1 minus half, which is a half. And we are done. Thank you for watching. If you enjoyed this, please subscribe, leave a comment and like. I'll be doing a lot more step videos, and thank you for your time.